Okay, so we are going to look at unit number 3 and lecture number 6. In the last class, we have seen the basic definitions of the switch level molding and how do we describe a circuit if the circuit consisting of switches, right? Now today we are going to see some of the examples as well as some delay concepts as well. Okay, switch level molding. Modeling examples and delays. Okay, fine. So let us write a simple Verilog program. Let us write a Verilog program. For 2x1 mux using CMOS switches. CMOS switches. Okay, so this is what the question that I have asked. So write a Verilog program for 2x1 multiplexer using the CMOS switches. Now how do we do this one? So 2x1 multiplexer we know in the gate level modeling, we know in the data flow modeling, but how do we design this one with the help of switches or the transistors? Okay, what to do with that? How do we perform this kind of information? Okay, so as all of you know that we have a 2x1 multiplexer, something like this, having one input is called I0, second input is I1, selection line is S, output is Y, right? So therefore 2x1 mux. So therefore what is the inside of the 2x1 mux? It's depending upon the designer. Okay, but my requirement is that we have to realize the 2x1 mux by using the MOS switches. So what are the different, what is the MOS switches look like? As we have seen in the previous class, it is a parallel combination of NMOS as well as PMOS. Okay, we have to consider a PMOS here, and parallelly we have to consider another transistor. So connect these two things here, connect these two things here. So this is actually the MOS transistor, sorry, CMOS switch. In generally we can call it as, it is N control, this is called P control, this is an input, this is an output, right? So now this is the switches he has asked to write a Verilog program. Okay, so therefore according to the truth table of this one is something like this. If S is equal to 0, Y must be assigned with I0. If S is equal to 1, I1 must be transferred. Okay, that is the shortest notation that we can give the behavior of the 2x1 multiplexer. Okay, as all of you know that the S can be used for the purpose of control. The inputs are applied at the input notation of the switch. So, okay, how many inputs are there? We have 2 inputs are there. That means that how many switches that we need to have? 2 switches are required, as simple as that. Okay, so we take a 2 switches. I'm going to copy this one. Copy and then paste. So this is a one switch. Okay, better to modify this switch itself. Okay, so I'm going to consider the input is here. I'm going to write my input. Input is I0. I want to write it here. Another input is here. This is called I1. Fine. Now the output must be a single data. Okay, the output must be a only one output. That means the output of these two must be short circuited, right? As simple as that. So take this one and connect these 2 points, something like this, and take a common point that is called Y. Now the question is, what is the selection lines that we have to apply? Okay, so therefore we have to manage these control lines. Okay, I naught, when it has to go to the I naught, as everybody knows that the switch is on, what is the behavior of the switch now? The behavior of the switch. What is the behavior of the switch? For example, n control nc I'm writing, n control is equal to 0, sorry 1, as well as p control is equal to 0, then switch is on. Switch is on. Everybody knows this one. In the last class we have seen. If nc is equal to 0 and pc is equal to 1, for example, the switch is off. This is what we have seen in the last class. Okay, so therefore that means that what we have to apply for the n control, logic 1 is required. Okay, so that means logic 1, logic 0, that is depending upon the variable, that is depending upon the variable called s. Okay, for example, if I write s here, for example, s here means obviously it becomes s bar. Okay, if write NMOS gate is S, the other must be S bar. Then only if S is equal to 0, for example, if S is equal to 0, this is off, as well as not of 0 means 1. For the 1, this is also off. Therefore, it is an open switch. So they cannot go, I naught cannot go in this way. Okay, therefore, what is the solution for this one? Everybody knows that it is S bar. It should be S bar. It should be S. Okay, if I put S is equal to 0 now, if I put S is equal to 0, if I put S is equal to 0, S bar becomes 1. Okay, therefore that means here if I put logic 0 here, it becomes 1. Ante kada? So therefore the switch is becomes on, therefore I naught will go. For I naught we are transferring somehow to the output side. What about I1 in that case? I1 in that case must be off. So if you want to say that this is off, what should I do then? What should I connect it to this? Anybody from the class? What is the best solution? I naught is moving from input side to the output side, right? Okay, but meanwhile I1 must be, that means this switch must be off. This switch must be off. Second switch, this switch must be off. Right, this switch must be off. So therefore what input that I should apply for this one?
Sir, S bar should be P control, S should be N control.
Yeah, S bar should be
P control.
The N control must be S, right? That's true. So in that situation, if I'm S is equal to 0, which means that this upper one is on, the lower one is off. Okay, therefore I naught will go. If S is equal to 1, for example, then what will happen? Upper one is off, the lower one is on. Therefore I1 will go as an output signal, right? So this is how we have to manage the input signals. This is how we have to manage the input signals. Therefore, instead of saying that these are separate lines, I can take something like this, okay? And I want to make it, it is an S bar directly. Or I can say that this is the best way. I'll write S something like this. This is my S, okay? And this should be NOT gate of this one, right? We have to apply the NOT gate to this one. Take this point, okay? Are you agree with me? Just only for simplicity, I'm writing all these things. NOT gate. Okay, similarly, S must be connected to the top of this one. Okay, again, the S is connected here also. I hope you understand the problem is. Okay,
Yes.
I'm saying that these things are available inside of your multiplexer. Okay, so therefore this is what your block diagram. So this is your block diagram.
So there not check could be also should be in NMOS or CMOS.
What is that?
Not get should be also NMOS or CMOS. No, sir.
Yeah, the NOT gate must be an NMOS only. This is the CMOS only. CMOS in the sense it's not like that. We have in the last class I told you that how to write the CMOS. Okay, so it is not possible to write that way. NOT gate means we have to consider one PMOS transistor, one NMOS transistor. Most regular switches that we have to consider. Okay, regular switches. So take a common point. This is called input. This is called out. Okay, this is what actually the NOT gate is all about. So it has only one input signal and only one output signal. But inside of this one, this is the block is there. Okay. For another method is also there to get the inverter. Okay. So other method into what is other method? So in the last class, we have seen that an OR gate, right? We have seen an OR gate. Okay. That means that, for example, A is input, B is input, Y is an output. So I want to convert it as an inverter. Okay, how it is possible? Take the same connection from A and B are the same level. Okay, then Y. So if you write A here, it becomes A bar. It becomes A bar. As all of you know that. But means already we have written the program for the NOR gate. Okay, we can use that NOR gate directly in this particular program, provided that input and output must be short circuited. So this is another method is there. Okay, if it is not method is not remember, it is not possible to identify, then the simple inverter is something like this: one PMOS transistor, one NMOS transistor. Okay, so let us write this program. All of you, please write this program. I have given the structure, and please try to write the program for this. So it is possible to write the NMOS switches directly, but we have a provision of using the CMOS switch also. The Vedla provides the CMOS switch as well. Therefore, we have to use the CMOS switch instead of NMOS switches, NMOS and PMOS switches. Okay, so if you are using the NMOS or PMOS switches, so we have to use two transistor top, two transistor bottom. Okay, so whereas if you are using the MOS transistor, it can convert, it will be converted to two statements only, two NMOS CMOS switches. Please identify that one. Okay, so before going to that one, first let us write the Verilog program for the NOT gate. Did we write the NOT gate program in the yesterday? Let me check. Have you written the NOT
No,
gate?
sir. No, sir.
We did not write, like NOT gate we have mentioned, but we did not write the program, I think so. Okay, did not write. Okay, let us write then. Okay, first of all, I want to, of course, this is actually inside of this one is like a switch level, structural level at the top. Top level is a structural molding. The basic level is a switch level molding. Please understand that point. Okay, so we have an additional component is there. NOT gate is available. Let us write a program for NOT gate. Okay, let us write module not underscore gate. We have an input, we have an out. Okay, what are the input signals here? Input, what are the input signal? In. So input and itla why it is we should not write? It is similar to that other switch, it is similar to that other keyword. That is the one point. Another point is that we have written I and in at the top level. So that the same name that we have to use. Please don't forget to write that one. But the better you can write it as in. Okay. And output is point out. Okay, point out. Right. It is mandatory to consider that the supply voltage also. Okay, supply one is actually high power supply one. Let us consider this is VDD line. Okay, and so what about the supply zero? All are small lowercase letters only. Don't think that this is uppercase letter. Okay, this is smaller case letter. This is also a smaller case letter, lowercase letter. Sorry, 0, and this is called ground. GND, ground, that I'm using. Okay, this is the additional things that we are writing in case of switch level modeling. Okay, again we write this one. What is the program for this? Before writing the program, first we should know okay what we can do then now. Chapali. So what will be the, what about the NMOS, sorry, PMOS switch rather? PMOS is nothing but PMOS. The name of this one is P1, for example. Okay. What is the output for this one? For the PMOS transistor, output becomes drain side. Drain is an output side. Source is at VDD side. Gate is at this point. Control is this one. First drain we need to write, right? So way to out that we need to write. What is the source? The input signal is
Out, sir.
yeah, out. VDD. Out is VDD. In is, sorry, out is out.
In,
In
sir.
is VDD.
Control. In.
Yeah, control. What is the control? In.
In.
Fine. What about P? NMOS. This is the name of this one is N1. What is the
Out, ground, in.
out, ground,
Ground,
in? That's true. Thank you. Okay. Finally, we need to write N module. How do we test this module? By writing the test bench. How we write the test bench for this one? Similar to that of what is the method that we have used for the gate level modeling, data flow modeling, the same method. But we don't want to consider the supply 0 and supply 1. Don't forget about the supply 1, supply 0 in case of writing the test benches. But in case of writing the module declaration, it should be required. Okay. Now, let us write a top module. So top module means this one. This is the top module, right? Okay, so better I am going to copy this one again, so that by looking at this one, we need to write the program. Okay, okay. Shall we write? Okay. What is the name of this module? Let us give. Okay, module. 2x1 mux underscore 2x1 underscore CMOS. That is the best thing that I have given. So it consisting of only I0 signal, I1 signal, S, Y. Everybody knows that input is I0, I1, comma, S. Output is Y. So do we need to write supply information here? Do we need to write the supply information here? No, we did not find any kind of power supply at this particular diagram. Okay. So therefore, this is not necessary. It's no need to write the supply 0 and supply 1. Okay. So in case of gate regular switches, when we are talking about the CMOS methodology, actually that we normally call it as. For that one, supply voltages are there, we need to write the supply. If the supply is not there, don't write the supply information, right? So therefore, just directly we can call first one. So this is called, for example, CMOS 1, for example. Okay, this is CMOS 2, for example. So let us write CMOS 1. Okay, therefore I'll write switches CMOS. What is the name of this CMOS? Let us consider C. It is not mandatory like this. It is optional. Everybody knows that. I told you in the last class. So this is writing this CMOS is an optional. Okay, just a second. Okay, fine. The battery is getting low, so it will be turn off at any point of time. That's the reason why I brought the charger. Okay, fine. So the next one, we need to write the what is the signal that we need to write for the CMOS? First, I need to write output. There is no option. So output, what is the output for this one? This is the only the output. That means Y is
Why?
an output. Y. What is the next one? Input that I should write. Input is I naught. What is the next one? N control or P control? I need to write from the you can see the syntax. So first N control I should write, then P control. I think so. I think so. Okay. For the N control, I did there is no name here. Okay. For example, I'll write as an X, for example. X, okay. Or I can simply write NC. This is called NC. I'll simply write NC, N control. Therefore, N control I'll write here. N control. Right? As P control is actually directly that is connected to S. That is directly connected to S. Something like this. NC, yes. Right? Similarly, for this one, CMOS, thanks for that. Thank you very much. Ramaya. Thank you. Okay, fine. Next, what is the next one? CMOS. For the sake of simplicity, I'm writing all these things, okay? So actually the CMOS 1, CMOS 2 is not necessary to write, or C1, C2 also not necessary to write. But better to write this one. When we are synthesizing these codes, these name of the devices are very, very important, okay? So let us write for this one. Again, Y here. What is the input? I1. What is an output for this one? Okay, if you NC is writing, that is name is suitable for that one, but this is not suitable for this one. But anyway, please try to understand the same name I'm using. Okay, and the selection line is, I'm sorry, it is not here.
Sorry, S comma
Yeah,
NC.
yeah, S comma NC. I think people will find difficulty in it. Therefore, I'll write it better. X I'll write. Okay, so I'm going to write it as an X. X here, X here. Okay, fine. That is completed. Another module is also there. Another component is also there. That is called not gate. So what is the name of this not gate that we have given? This is the one, not underscore gate. So there should not be any kind of space between not and gate. The same name we have to use, right? So let us write that name, not. Actually, it's not a keyword. It is defined somewhere. That's the reason why. And what is not underscore gate. So let me call this is the name module number 1, for example. and it starts with input and output. What is the input for this gate? The input for this gate is actually
Yes.
coming from it.
Yes.
Yeah, exactly. It is S. Not what is the name that we have given first? Input we have given, output we have given. Fine. S is the input for this one. What is the output for this one?
X.
That's it. So this is an AND module. Okay, so don't forget to write the test bench for all these things. And wire is also required for this one, right? Don't forget to write the wire. So wire X. So therefore, this is the structural molding actually. The top level is always the structural molding. Individual components can be written in any method, okay? But in this particular case, so switch level molding is a suitable one. So this is how we need to write the switch level molding for this one, okay? And let us write another one, another program. Let us write second program. Write a Verilog program. For D-latch, for a D-latch using CMOS switches, Okay, therefore, a little bit we are going to the concept of sequential circuits, but the sequential circuits are best defined in the behavioral modeling. We will see that one in the next class. Next coming classes, we look at that one. So for the time being, just please let us design this exclusive OR gate. Sorry, this D-latch. Okay, everybody knows that. So latch is nothing but it is used to store the information. Okay, so as long as the signal level is high, when the control signal level is high, the information will be retained or maybe transferred. If for example, in the case of high level language that we are high level we are considering, whenever we have a high level of the control signal is there, then the signal will be transferred. If the low level is there, the signal will be retained. Vice versa is also possible. Okay, so that details also we will look at in the later on. For the example, let us design this one first of all. Okay, so the design part you don't know. That's the reason why I'm telling you. For example, if any logic gate, if you consider something like this, okay, and take an output something like this. Whenever we are giving input signal input here in this way, in instant of the time, if you are getting the output, that is called the transformation of the data is possible. This is simply a combinational circuit. For example, if you want to keep whatever the output is there in this block itself, then what I can do is that I want to retain this information in this block itself. Okay, whatever the information, it doesn't matter. Of course, it go to the output side, it doesn't matter. But I want to keep the same information within this one. Then what I have to do, I have to use the method called feedback method. Okay, therefore what I can do is that the same information I'm going to feed back to this particular input. Okay, so therefore this feedback mechanism, whatever the output is there, that output will be retained here. So whenever you are giving somehow some by means you are applying the input here at this place, that information will be available within this block itself. Okay, therefore as long as this feedback is existed, okay, the information will not be loose in the design in this particular block, right? So therefore this is the method that we have to use in order to store in order to develop the what we can say that in order to develop the memory element. Okay, so let us write this one. First of all, I want to use the transformation of the data, right? So the transformation of the data. So what I can do then, so simply I can use for the transformation of the data, simply I'm going to use the CMOS switch. Okay, I'm going to use the CMOS switch. Okay, see what is happening here. If whatever the data is there, the data will go as an output side. Okay, Data in, let us consider. This is called data in. Data in go as an output, data out, provided that the control signal must be given in a proper manner. Okay, if the control signal is not proper, then cannot be go. For example, the control signal is, for example, a clock signal. Here I'm writing a clock. Clock is since CLK, normally people will write. That's the reason why I'm writing the CLK. So what should be the PMOS clock then? PMOS clock must be clock bar. Antena? So then only the data in will go as an output signal. Right. So therefore, the usual practice is that whatever the output is there, that output we take it through the inverter. Okay. So output is taken through the inverter. Okay. So whenever we have switch level designs are there, usual practice that they will consider it for the NOT gate at the output side, so that the information will be, if there is any degradation is there, the degradation will be retained by the NOT gate. Therefore, they have to use the NOT gate at the output side. Okay, fine. So in order to send an information inside of this particular one to the output side, actual original output is this one, original output. Data in signal will go as to the output side. This is the method that I'm using. But I want to say that once the data is sent into the device, that means up to the point from point A to point B, for example. So point A to point B, I'm sending the information. But after inserting the data inside of from point A to point B, there should not be any kind of role for first CMOS. Okay. So when we are the transformation purpose, I have to use this one. The first one we have to use. For storing purpose, I don't want to use this one. Okay. So that means that I need to give the feedback, right? So somehow I have to give the feedback from here to here, right? So if I use the feedback something like this, it is always something like this only. Okay. There is no control on the storing of information. We don't have any control on this storing of information. That means input istaru adi aa block lo rotate avuta untadi, but that is not the case. So the storing has certain amount of the time the storing must be there, certain amount of the time the transaction has to be possible. Okay, so for example something like this, if you take one the clock signal, for example, a clock signal. So during this during this time the transaction has to be takes place, during this time storing has to be takes place, or during this time storage has to be takes place, during this time transaction has to be takes place. Okay, so therefore it is not by this connection, whatever the connection that I have drawn here, it is always storing the information. Okay, once you give the information, that retains there, that's all, but it's not the obvious solution. So what we have to do is that we need to remove this one. We have to put some control on this feedback path. We should have a control on this feedback path. How do we do this one? So for that one, I'm going to consider another switch here. Another switch here. This decides that one. Okay. Once the data in is enter into this particular from A to B, during the time, there should not be any kind of feedback path. Okay. In order to do this one, that means I need to connect it here. For example, the feedback path, I'm using something like this. I'm using the feedback path something like this. Okay. So that means whenever it is a transaction takes place, there should not be any kind of feedback path, right? So if you want to disconnect this feedback path, what should be the control signal for this one? Is it a clock bar, right? Is it a clock? Sorry, it is a clock. It is a clock bar. Please observe. When the clock signal is equal to 0, 1 for example, which means that out is equal to, output is equal to data in, that's what, data in. So during this time, what is happening here? Data in. During this time, what is happening? Feedback path is disconnected. feedback path is disconnected. So this is the obvious solution. Okay, in the direct connection means that the clock is equal, output is equal, DN will be happen, but again it is stored directly. That should not be happen. Okay, when transaction is happening, during the time feedback path must be disconnected. That is a good solution, right? So that's the reason why I'm going to use this one. And one more thing is that whenever the data is available here, it is a complemented output we are getting, but original output that I need to have. So in that situation, what I have to do, again, if you want to store the original data, whatever the data that I'm giving, I'm going to consider another NOT gate here as well. Another NOT gate. Okay. So this is how I can connect my flip-flop. So see here, for example, if the clock 0, 1 case we have written. If the clock is equal to 0 case, that if you write, what will happen? What will happen? Output is equal to output, right? During this connection, transaction is not possible. Transaction is not possible, which means that storage is applicable, right? So therefore, this is the time when this is the time the transaction should not be happening. Clear? So this is what the designing part of the D-latch. Okay. So therefore, what we are saying that whenever we have a clock something like this, whenever we have a clock something like this, during this time, what is happening here? During this time, storage. What about this one? What is the what about this duration? Transfer. Okay, that is what the sequence is happening all the time. And as long as the clock signal is equal to 0, logic 1, logic 0, logic 1, these things are happening. Okay, of course, the storage is actually, we want to keep the information for a long time, then the flip-flops will come into existence. But for the time being, this is actually simply a latch. That means the storage time is only half of the entire clock period. Okay, if you take this is the period of the clock, okay, time period, only half time that we are going to store, or maybe less than that of half also, according to the diagram it shows that. Okay, so I hope you can understand the concept here. Okay, what is the block diagram for this one? The block diagram is something like this. So it has a D input signal, the data input signal, for example. Please try to understand. Next one is a clock signal. The next one is output signal. Output, instead of writing output, out I am writing. Okay, so therefore, what is the inside of this block? So this entire thing will be there. Okay, you have to write the program for this one. Clear? So how many NOT gates are there here? How many NOT gates are there? NOT gate 1, G1, this is called G2. Clock to clock bar. Again, we have one clock is required, one NOT gate is required. Okay, 3 NOT gates are required. Please remember that. 3 NOT gates are required. So therefore, that means I have to write something like this NOT gate here and go to this C bar. And again, this C bar is also coming at this point also. So according to this one, we have to write the Verilog program for this one. Okay, it's not all the time to write the Verilog program. So it's very difficult for me to write all the time. So this is the basic background. You have to write the program for this. Okay. If you have any doubt, we will discuss that one in the next class. Okay, fine. Next, let us go for the delays involved in this particular switch level modeling. Okay, let us write the delays. Okay, so before going to the delay of the switch level modeling, let us talk about the gate level delays. Sorry, already gate level modeling చదివేసాం కదా. We talk about data flow modeling. Data flow. Everybody knows that. What do you mean by a delay? I told you that. Okay, so what are the different type of delays that we can see in the gate level modeling? That is also we have seen. So all these gates, what we can say, all the gate concept, all the gate concepts, gate delay concepts are applicable here also. Okay, applicable here as well. You don't forget about this one. What are the different delays are there? Raise delay, fall delay, turn off delay. Okay, so if you are, it is possible to give the one delay. You don't want to give the delay means instant delay. There is no delay at all, no delay. What are the possible delays? Let us write. Let us recapitulate. What are the possible delay? Zero delay. That means we are not going to introduce any kind of delay value. And one delay, what it says that one delay, it says that the delay of rise, fall, turn off is the same. Two delays, what we can say that, so rise delay is we are specifying, fall delay we are specifying, but turn off delay is not specifying. It's a minimum of the rise and fall. Okay, three delays also there. Three delays also there. So that means that we are implicitly specifying the rise delay, fall delay, and turn off delay. Okay, so if you go a little bit more further, the delay concept means we talk about the minimum delay, maximum delay, and yeah, the turn off delays as well. Okay, so the same concepts are applicable here, but for the sake of simplicity, I'm going to tell you another point here. Okay, normally we have implicit and explicit delays. What do you mean by this? What's the names, technical names, these are all, nothing more than that. For example, if I write like this, example, while C, okay, assign, so the delay is given in this method, in this way, ash 5, okay, y is equal, sorry, C is equal to A comma B. C is equal to A and B. Can I write like this? Initially, what we have seen that assign C is equal to A and B that we have written in the continuous assignment statement. This is the methods that we are using. But now, this is some delay is involved in this one. Some delay we have introduced. So how we have to give the delay for the assignment statement? It goes something like this. Just after the assignment, we have to give the delay value. Okay, so is it zero delay or what delay this is actually? It's a single
Five.
delay, one delay. Okay, one delay. One delay means what we say that 5 nanoseconds or 5-10 minutes for a rise delay, fall delay, and turn off delay. Okay, for example, if I'm not writing anything here, for example, so what is the delay here now? Zero delay. That means that whenever we are computing the A and B, does not have produce any kind of output, does not produce any kind of delay. Instantaneously output we will get there. But the Verilog is providing, it's not because any computation does not, we cannot say that it is a very instant output they will give because of their parasitics. So obviously some delay will be involved in this one. Okay, whenever we are providing A and B computation you are doing, it takes some time. Therefore, the time we are modeling something like this by using some delay value, right? Fine. Next, for example, so this is called actually an explicit delay. We can call it as an explicit delay. That means explicitly we are writing the delay is something like this. Okay, my output signal is directly I'm writing explicitly something like this. Or it is also possible to write in this way also. While ash 5C. And you can write directly assign here something like this. Assign C is equal to A and B. Something like this I can write. Okay, this is called implicit representation. Implicit representation. That means we are representing the output 5 at earlier stage. Okay, it is called implicit representation. So that means the operation is the same. There is no doubt at all. The operation for this, whatever the output that we are getting for this first case, whatever the output that we are getting for the second case is the same. But how we are representing the delay is the, technically they are, the people will call it as explicit delay. This is called explicit delay. Okay, na? అర్థమవుతుంది కదా? So that's how we can do. So therefore, anyway, the rise delay, fall delay. So let us consider, for the sake of simplicity, I'm going to write another statement, assign. I want to make it comment. For example, 5 comma 2, C is equal to A and B. For example, something like this, right? So they have given the 2 delays, like 3 delays also I can produce. Okay. So let us take one example. I want to make it one definition here, so that I'm going to consider one example. Example 2. So it is an example 1, example 2. So with the help of diagrams that I'm going to write this one. For example, something like this. For example, A is something like this. Something like this. B. So for example, this is A. Okay. The B is also something like this. Okay. Na? So therefore, the time delays, time values are something like this: 0. This is the 10. For example, this is the 10. This is 20. This is 60. This is 80, 85. Okay. Na? Okay. So for example, if I'm writing 10 value, let us give the 10. Okay, 10, let us give. Wire 10, this is called B, for example, is a B. 10, C, for example. Assign C is equal to A ended with B. C is ended with A and B. Okay. Now let us write the output for this one. Okay, what is the output for this one? Any guess? So it is started at 0, right? It is started at 0. The C value is something like this. So whether it is explicit delay or implicit delay, so it is an implicit delay, because I'm not giving the delay value directly to the assignment statement. For output, the way the output is there, for that one I'm writing. Okay, therefore this point to the 10 nanoseconds, for example, here is the started of 0. Okay, this 0 is not evaluated and give it to C directly, right? So that means here we have to say the 2 points that we have to remember. One is called evaluation. The second one is called assignment. So this is what actually the involvement of the assignment statement. That means evaluation means A and B must be computed first. A and B must be computed, and that computed result will be assigned to the C according to the delays that is given. Okay. If it delay is not there, directly it will be assigned, otherwise it will be there. Okay. So A and B will be evaluated, but that is not assigned to C directly, but it waits for 10 nanoseconds. Okay. So for example, here is the 10 nanoseconds. That means up to that point, the value of this one is unknown. At this point, I'm sure that the logic 0 is existed for the C, right? Now the 0 is available. Now it is go on. Okay. At 20 nanoseconds, for example, this will be the 20 nanoseconds, for example. At 20 nanoseconds, it identifies that there is a change in A and B to logic 1. So what is the end operation between A and B when A is equal to 1, B is equal to 1? Obviously logic 1. Is this logic 1 is assigned directly to this one? No. It has to wait for another 10 nanoseconds. Therefore, it has to wait for 10 nanoseconds, which means that 30 nanoseconds, right? At 30 nanoseconds, the one logic 1 will be assigned there. Okay? Are you agree with me? Are you following this one?
Yes, sir.
Yeah. So now this is the logic one. It is go on and go on because there is no changes from A and B and go and B. At 60 nanoseconds, again, it finds that there is a change in A. Okay, but there is no change in B. Anyway, explicitly, if A and B are changing, this way, this assignment will be computed. Okay, again, there is a change here. Okay, what is the value of this one? It has to go to logic 0, but it cannot go to the logic 0 instantaneously, but it has to wait for another 10 nanoseconds. So other 10 nanoseconds. That means at 70, it will go to at 70. It is at 60. It is at 30. Okay, it is at 20. So it is at 10. It is at 0. Okay, now what is the value? It go to logic 0, something like this. Okay, again it is going 0 and 0 and 0, 0, but 80 nanoseconds, at 80 nanoseconds, exactly at 80 nanoseconds, it finds that there is a logic 1. Okay, logic and logic 1 means what is happening here? Babu, please carefully understand this one. It is a logic 1, this is also
One,
logic 1, 1.
one,
So therefore it has to assign to the logic 1, but it cannot assign to logic 1 directly. It has to wait for
10 more seconds.
10 more seconds. That means at 90 nanoseconds, for example, at 90 nanoseconds, this value must go high. But meanwhile, see, if it's at 80 nanoseconds, you find again there is a change here, right? Very careful understand. At 85, we can find a change here. Okay, but this change cannot be taken into consideration. Okay, because this duration, the pulse duration is actually 5 nanoseconds, but the delay assigned to the assignment statement is 10 nanoseconds. Okay, so therefore, whatever this short duration pulse does not affect the operation. Okay, therefore, what is happening at 80 nanoseconds, if we add for 10 nanoseconds to this one, it will go to the 80. But we have 85, we have a signal change, but it may not be considered. Okay, so it has to go to the logic 1 again. Okay, so logic 1 is obtained at this point. Okay, is it clear? So that is what we have to understand about the delay concept here. So therefore, this is called inertial delay. Inertial delay. This is called an inertial delay. So can anybody tell me inertial delay means? Inertial delay means if the input pulse duration is lesser than that of the delay of the assignment, then the pulse variation does not take into consideration. Is it clear? So that's what we can say that normally actually at the 10 nanoseconds, if we'll go to the 8 nanoseconds here up to this point, at again it has to go to 0, and 0 means 95 nanoseconds it has to be evaluated. But instead this value will be in whatever the value is there, that this particular change does not affect the output. Okay, because of its pulse duration is less. Okay, so therefore I am going to write one statement here. What is the pulse duration statement? Just a second. Okay, so this is called an inertial delay. It is called inertial delay. So shall we write the definition of the inertial delay? An input pulse that is shorter than the delay of the assignment does not propagate to the output. Okay, that's it. So we will see the remaining things in the next class. Okay.